Okay, so this is not on the topic, but since it just came up, this is paint. And where do you see the linear algebra in paint? It's very small, but it's right here. So at the bottom, it gives you that gives you the size of the image. The one on the left, it gives you the location of your mouse, right? So left, right. So you can do all kinds of measurements using that with any accuracy. And just it's all upside down in comparison to what we're used to, because it measures down and right rather than up and right. Okay, so you can also view, you can have grid lines. Okay, so that's what it is. In the coordinates, you can draw a straight line, and other lines. And so, well, you can do this. If you're interested in a vector, here's a vector. It also gives you in the middle. It gives you the x and y components of this vector, right? This is the number. X component, y component. They don't understand negative though, so that's keep that in mind. And if you already have something drawn, you can literally use this to measure it, at least in relative terms. Okay, so that's what the way to solve number 4 problem from the last homework. To copy the image, to paint and do measurements. But as I said, the idea is that the really what's educational here. What is it? What's to be learned is that you can't do it without linear algebra, or at least the coordinate system hidden somewhere inside of Excel or anything like that. So if you do computer animation or any kind of imagery, then you're going to do this, but really it is going to be three-dimensional, right? You cannot really do animation if you are, even though everything ends up on the two-dimensional screen. What was behind all the motion and measurements and shadows are all done three-dimensional, and you need to really think about perspective. So how do you create perspective on in that image? So I do understand that they do three-dimensional simulation or modeling, which then projected in the two-dimensional. It's like different cameras. You can measure. You can film the same animation to producing two different films of the same whatever is being transpiring in the story. You can create different screens, and then perspective, shadows, all of that has to be represented appropriately within the coordinate system. So this is just the very basic, but it gives us n-dimensional stuff as well. So okay, so what we're studying here is we study subspaces and how we need to learn to treat them the same way we have treated the Euclidean spaces. So which means that in addition to the standard basis of the Euclidean space, the one that you see here, the standard basis of the Euclidean space R2 is these two vectors. But what if we encounter spaces also that are not given in that explicit way, in the simplest way, but they come possibly from solving system of linear equations? We have to also express be able to express every vector within that subspace as a linear combination of these. Okay, so and that's why we end up with the concept of basis. Okay, so this is the concept of basis. Vectors that do what? Every vector in this subspace can be represented as a linear combination of these, but you cannot remove any vector, which if you do remove any vector of this collection, then that property fails. Okay, so in other words, how do we express this? We would say that V1 So in other words, V1, Vm spans V. Okay, so that's what span means. The span of these vectors is V, which means that every vector in V can be represented as a linear combination of V1, Vm, but also without redundancy. Okay, so that's another way you can that idea can be expressed. That's what creates a basis. That's the idea of basis comes from. But at least as important is what we gain from it, and that is the concept of dimension. So that way we can distinguish between bigger and smaller spaces or subspaces. It is the dimension, the number of degrees of freedom in that space. Okay. So let me examples that we have had illustrate that idea. This one is at the bottom is especially simple. So the standard basis on the left and non-standard basis on the right. As you can see, what makes them a basis, because even though they are not perpendicular is not important. So the two vectors on the right, V1, V2, they're not perpendicular yet. However, we have demonstrated right here that every vector can be represented. Vector AB on the right, see over here, I'm trying to represent vector AB as a linear combination of these two, V1, V2. Okay, and indeed, can it be done? Well, I create a system of linear equations and solve it, and turns out that yes, it is indeed the case. Okay, so then turns out that's why we still would have to make sense of it. We would have to demonstrate that there is I mean, if you have two bases of the same space, look at these, they would have the same number of elements. It's certainly not entirely obvious, but that would have to take a different kind of linear algebra course to prove all of those things. Which means that not only all the bases have the same number of elements, but also of the same space, but also that's why the dimension makes sense. Dimension is the number of elements in the basis, in a basis. So if you look at this picture, you can figure out why one vector would always be not enough, and 3 will always be too many. Right? Well, we talked about one vector cannot possibly give you the all vectors on the plane as linear combinations, because one vector is simply, its linear combination of one vector will be multiples of that vector. So you not get everything. Why 3 is too many? Well, because 2 is enough. Because you can always express the third vector in terms of as a linear combination of the first two, and then you can just throw it out, and it's of no use to you. Okay, so that's roughly how it works. There's a theorem that summarizes this idea and also connects it to the idea of linear independence. Because what separates, if you pick two vectors on the plane, what is that? How do you recognize, they don't have to be perpendicular, right? Okay, how do you recognize a basis? So, and the answer is they have to be linearly independent. So, so if the number fits, such as 2 for the plane, then you still need one more requirement to be satisfied, and they cannot be multiples of each other. So, if it is a three-dimensional space, you have 3 vectors. How do you know that they form a basis? Well, they should not be linearly dependent. That linear dependence, that is just another way to describe redundancy. If they are linearly dependent, then one of the vectors is expressed as a linear combination of the rest, so it's of no use. Okay, so as a element of a basis. So this is what the theorem sounds like. Comparison theorem. So V is number 1 property. V is the span of V1, Vm, firstly, and secondly, we have vectors W1, Wn, They are linearly independent. In V. Okay, so V is a subspace. That's it. Okay, so it has no structure to begin with. So that's the difference from the Euclidean spaces we looked at the very beginning. They came with a structure, meaning they already had that standard basis. Okay, now but this V, where it has come from, we don't know. Maybe we have solved the system of linear equations. We don't know anything about it, about its dimensions specifically. But this is, we have a span by m vectors, but they're not necessarily a basis. So, and I'm not saying that this is a basis, but they suppose they span the whole thing. So once again, every element in V is represented by a linear combination of those. Then, okay, well, can you tell me the relation between n and m? Based on this? Well, let's approach this way. Suppose the dimension, as a part of, let's just analyze this. Suppose dimension of V is, say, D. Dimension of V is D. If we look at number 1 statement, compare D and M. D and M. So the V is spanned by m vectors. What does it tell you about the dimension? No, not necessarily the same. Those vectors V1, Vm might be redundant. We are not saying this is a basis. We're only saying that it spans the whole thing. So that condition that it cannot be redundant is omitted. So it could be larger. It could be larger. It could be, that is the redundancy. You could have more elements. You can span with as many elements as you want, and there is a basis somewhere in that collection, as a matter of fact. But it could contain some redundant elements as well. Okay, so if you have a collection of m vectors that spans the space, then you have it means that you have to have at least as many elements in the collection. So you cannot have fewer than D. Okay, so that's what the definition says right above. And now what if we compare N and D? N and D. So property number 2, or rather the collection number 2. W1, Wn are linearly independent. If the space's dimension is D, how many linearly dependent vectors can you have? Well, there is a limitation of the number of linearly independent vectors. So on the plane, you cannot have 3 linearly independent vectors. You cannot have 4 linearly independent vectors in space. So if these are, I take any 4 vectors right here, they are linearly dependent. Okay, always. For 4 vectors, you cannot have them linearly independent. Well, it's less obvious then, but in dimension, probably the better example is dimension 2. So on the plane, try to put 3 vectors on the plane like this, and then they will be linearly dependent. So you can pick one and express as linear combination of the rest. Okay, so probably you can have a picture. So once again, this is a plane. I have 3 vectors, arbitrarily written, and then if I say I pick these 2 and I'll tweak them around a little bit, change the multiples a little bit, and can, well, that's what the homework was, right? So you had the 3rd vector, and you had supposed to be, they were chosen arbitrarily, and you were supposed to express it as a linear combination of the other 2. And you can certainly, that probably wouldn't appear if it is not less than or equal to right. It cannot be larger than the dimension. Okay, so that is what happens if the dimension is known. Then you cannot have fewer than D vectors to span the whole space. On the other hand, you cannot have more than d linearly dependent vectors. Okay, if you put these together, if you take these two together, then you have the definition, right? So it is simultaneously. What is the basis? This is the basis. A basis that is simultaneously satisfy both of these two properties. It spans the whole space, and it is they're all linearly independent. Okay, so that's the idea of the theorem, and then the inequality will be that you cannot have n large smaller. So this is the inequality. I'm sorry, the opposite. Let me see again. Let's confirm. So M, the span is, yeah, okay. So that's why, in particular, if you have an n-dimensional space, you cannot have inside of an n-dimensional space an n+1 dimensional subspace. So it is a very strict hierarchy of spaces. That's why things work together. Okay, so back to this topic of linear functions. So we try to discuss, even though all the time we have spent talking about bases, what if we have a subspace that is not does not have a chosen basis? Okay, so because as we know already, bases, there may be infinitely many bases. Probably worth discussing separately, but since we started with a function, suppose the basis has not been specified, and that is if you think about it's not really such a common occurrence if you're talking about, say, calculus, that you always have the x-axis, you have the y-axis, all the units have been specified, which means literally that suppose this is what we're talking about in calculus, x and y. This is what has been supplied. Look at the things that we're facing. With this, so this is the picture coming from calculus 1. This is this, right? This is calculus 1 picture. Now, if I interpret this picture in a linear algebra sense, it's exactly the same thing, except these are the basis vectors. You can see where they are the unit vectors that go along the axes. Okay, so calculus 1, and this is linear algebra. And you can certainly go back and forth, but if we go from calculus to linear algebra, we simply take the vectors, unit vectors along, that's what a standard basis is, the unit vectors along the axes in any dimension. Along meaning that they follow those arrows, right? So if you have axes, if you have now three-dimensional space, you'll have three unit vectors along the three axes. Okay, but hypothetically, the functions are really not about that. They're if we think of functions as transformations. So what I'm talking about is, say, f from v to w, two spaces. So input space, output space, both of them are Euclidean spaces or subspaces. Okay, so then we could try to describe things the way we have, and we can think of it as a transformation. And it can be described without invoking the basis. Okay, for example, f of x is equal to 0. That is the simplest linear function. The simplest linear function is, or any function, the simplest one is simply all values are equal to 0. Okay, that's a function for you. Or it could be, so the 0 function. Remember we talked about the collapse of the space to a point. That's what it is. Another example, if my function is from the space to itself, it just happens to be w to be the same, we can define f of x equal to x for all x. It's called the identity function. So once again, the point of these examples is pretty much that to point out that there is no need for a basis, specified basis, in order to define functions. It's like a piece of paper. Do I have this? Suppose this is my v. Do I need for what I do need it if I have my v. Let me maybe put it like a piece of paper. Suppose this is a two-dimensional space. Okay, so what do I need really? Only one thing, and that is for sure I'm going to need the origin. Okay, so then with the origin I have all the vectors in the world available to me. Okay, and then so these are the inputs. And then just happens to be two-dimensional. But then I will have my function that f. And suppose the output space is also, well, just hypothetically also two-dimensional because it's easiest to visualize. So dimension of w is also equal to 2. So once again, what do I need? I need the origin for sure, and then the rest, and then I have a bunch of vectors all everywhere. So these are the outputs. So one vector on the left is taken by f and creates some new vector on the right. That's what the function is. From one set to another set, functions to functions. Why do I? That's it. That's it. We have two spaces. Each of them could have infinitely many bases, and without specifying the basis, we still can create at least these two functions. We can create others, right? We have seen already examples. You remember other examples of a transformation like that? Dimension 2, dimension 2. What others? What transformations do you remember? Well, the examples that we looked at were between between R2 and R2, but we are past that. Okay, so that was the original examples that we looked at was from R2 to R2, and we were able to have specific formulas there. But it is also possible that we're not looking at specific Euclidean spaces with specified standard bases, but rather two subspaces, which just happens to be two-dimensional. That's all. So that's why I don't need a formula to say, for example, f could be a stretch. Okay, stretch, possibly non-uniform stretch in different directions. It could be a stretch. It could be, remember, a rotation. Remember the third? One more transformation that doesn't fit the list. Stretch, rotation, and no, shrink is stretch. What? No, shift. No, shift. Generally speaking, yes, you can shift. But if we're studying linear, we are still sticking with linearity. Think about what happens if I take that that orange vector over there in V and shift it. It will not be at the starting at the origin anymore. So we are deem those nonlinear. Shifts are then nonlinear because they do not produce vectors that start at the same point. So rotation, right? The vector will remain centered at the origin, starting at the origin. Same with stretch. There's one more.
Inversion.
There's a better word for it. Unless, what do you mean inversion? What?
Reflection.
Reflection or flip, one of those. So you can see that you cannot stretch something into reflection or rotate. Rotation and reflection might sound similar, but rotation is within the plane like this, and flip is this. Okay, changing the, flipping the orientation. So this is pretty much what we're after. Okay, so these are three main examples. It actually can be demonstrated there is nothing but these three just combined together. So whatever linear transformation we have, it will be a composition of these. But before we get to that, we got to decide what a linear function is. So what is a linear function? And first of all, we gonna deal with the terminology, and that throwing out shifts is something that is not done in calculus. So for example, mx plus b, we talked about that already, but let's do it again. Is linear, is the way I'm going to put it, is a linear function in calculus. And yet we want to throw it out because shift will not produce a new vector starting at the same point. Okay, so then we will be referring to mx. That would be fine. That's a stretch. Okay, so that's fine. And I will be referring to them as linear operators. Okay, so this one is linear for sure. But how to distinguish between the two so there will be no confusion. It is common in linear algebra to refer to what we actually wanted to study as linear operators, which is just a fancy word for function. Okay, and the answer is, this is the definition, a tough one. A function is linear if it is it preserves linear combinations. So f from b to w is two subspaces, is a linear operator. If f preserves, so that's just the language we use to describe it verbally, but then you need a formula, preserves linear combinations. So first of all, before we get to formulas here, it's not entirely new. We'll see that this is not entirely new idea, because if we just go backwards a little bit and realize that linear combination is just two algebraic operations combined together. It is addition and scalar multiplication. Addition and scalar multiplication. So if you take them together, you get yourself a linear combination. So x plus y or ax. Okay, so if you combine these together, you have ax plus by, a linear combination. So addition, scalar multiplication, linear combination. So we just combine them together, so just to make it slightly more compact, but it is what it is. So if you go back, then you think about addition, and then you might remember some from calculus, some functions that preserve addition, and some functions preserve scalar multiplication. How about differentiation? We're not going to look into spaces, vector spaces of functions, unfortunately, because those are infinite dimensional, but it is actually a very, very solid application of linear algebra that pays back to calculus, and that is thinking of functions as vectors, as well as differentiation and integration being linear operators on that space. So that is the bird's eye view of calculus, which you cannot have without linear algebra. Okay, but we'll concentrate on finitely, as we have on finite dimensional spaces. Finite dimensional spaces meaning that a basis has finitely many elements, and unfortunately functions cannot have that, and so they are infinite dimensional, unfortunately. So anyway, so what does it mean? What does it mean to preserve linear combinations? It is f of x plus y is equal to, once again, if I am looking at addition, f of x plus f of y. That's how you preserve addition, and this is how you preserve scalar multiplication. It is. I really cannot think of anything else maybe to connect to these ideas other than the differentiation. Limits, differentiation, integration every time. So you do addition. There's a sum rule. Remember, sum rule, constant multiple rule. So that's what happens. You differentiate a function. What do you do to it? If you have sum of two functions, nothing. You just break it into two. Okay. Same with if you have a function multiplied by something. What do? You just factor it out. Okay. So it is certainly very easy to demonstrate that that function we looked at, mx, is a linear operator in that sense, and mx plus b is not. Okay, so for example, mx plus x prime is equal to naturally mx plus mx prime. That's an example from dimension 1 algebra, or max. So my function is simply multiplication by m. So I can certainly factor things around any way I like, and that's the how I preserve linear combinations in the one-dimensional situation. Okay, so so that's the simplest example of a linear operator in dimension 1. If we look at things that are slightly more complicated, then let's now jump to a two-dimensional case, and those examples are, well, is it obvious, you see these examples right here, is it obvious that these will be linear operators? Well, let's pick one. Let's pick rotation. Do you see why rotation would preserve linear combinations? So why does rotation preserve, in that sense, let's just say addition of vectors?
Because everything rotates.
That's right. That's the way to describe it. So so you take you have two vectors, say x and y. You add them together, you get the third vector, x plus y. This is happening in V. Okay. Now rotate. What you rotate the whole thing. So not only x will be rotated, y will be rotated, and their sum will also be rotated. It's just literally like a piece of paper. I drew this on a piece of paper, and then I rotated it. So maybe this is my piece of paper, like this, okay, in V, and then I rotate it any degree I want, and let's say maybe just a little bit, just rotate it a little bit to the right, counterclockwise. So I have x a little bit rotated, okay, y a bit rotated, maybe like this, and then this one will be rotated just as well. So let's be specific here how it works out. Well, my picture actually is not good. If I want to do addition here, this is how it works out. I have my parallelogram, and this is my sum, like this. So my parallelogram gets rotated. If x is rotated and y rotated the same amount, then well, the whole parallelogram will be rotated. So so once again, that's my piece of paper rotated slightly this way. Okay, we're rotating, naturally we only talk about rotation around the origin. So any other point that will ruin everything. Think about scalar multiplication, same story. You draw, you double a vector, and then you rotate everything. Well, it's still double, remains double. That's what happens when you talk about what is so special about rotation. It's really, it's motion. It's motion. A piece of paper is being moved. Since there is no shifting, there is no that's out. But rotation, as you can see, it is literally a motion. Nothing changes as far as even distances do not change between the points. So it is identical. What would you say? You would say probably that the triangles are what to each other? How do they related to each other? Let's say, I don't have yellow. Shit. Say this triangle and that triangle. What do they have in common?
Same area.
Same what?
Area.
No, more than that. What? It's the same triangle. It is the word is congruent, probably, if you like that word, but it is the same triangle indeed. Congruent meaning that you can it means what we just been talking about. It can be overlapped. If you move it around and overlap, then it will work out just fine. So that's what it is. Because it is motion. There is no change of the sizes, dimensions of the object that you're looking at. Same with reflection. Reflection is also motion. So once again, there is no stretching. You just flip it like this. Nothing changes. That same picture, you just look it through to the light, and you can see the same picture. These triangles will remain, and the sum will remain where it was. So there you go. The only question is the stretch, and that is not entirely obvious how it works out. However, what if we stretch proportionally to begin with? So if I take that picture over here and stretch. So in other words, I will, let's say by 2. Say the factor is 2. Where's my thing? What happened here? Here it is. Okay, so I have, well, let me try actually to make the point clearer, like this. So I take this, copy, and paste. Okay, and now I'm going to be stretching it. So I'll try to stretch it exactly by 2. Tell me if I'm doing it right. Okay, so I stretch it proportionally. I think I stretch it proportionally. Okay, so it's not the same triangle. It's not the same triangle anymore, that yellow one. What is the relation?
Similar triangle?
These are similar triangles, right? Indeed, all the dimensions change by the same coefficient. So those are similar triangles. But other than that, as you can see, what was, if it is a parallelogram, it is still a parallelogram, and the diagonal of the parallelogram remains the same, so that's why the summation remains where it was, right? So my x plus y is still there where it was, and indeed it gives me the addition. Disproportional stretching might take some effort to see that it preserves the operations, but we'll see that. We'll certainly demonstrate that eventually. So stretching, rotation, reflection. These two examples are obvious. The two examples, the 0 even though they're not motion. So everything goes to zero. Everything becomes zero. Then, of course, it doesn't matter what the values are. 0 plus 0 is 0. So 0 multiplied by anything is still 0. So the number one example over there will also preserve all the operation. And the next one is nothing to worry about because it's not, changes nothing. It's literally changed. There is no rotation or stretching anything. So certainly preserve everything we care about. So it will require some proof, but at least we have a bunch of examples that are linear operators. Okay.